today we are going to take a look at 1.5, so second to last section for the week. And this is on transformations. So we're going to study transformations with every kind of function we do. Right? Each chapter we look at different functions. This particular section we're going to look at transformations, and we're going to do them with quadratics, okay, with parabolas. So the basic transformations we can do are like shifting left and right or up and down. So that's horizontal and vertical shifts. We can also do stretching left and right and stretching up and down, vertical and horizontal stretches. We can also do some reflections, so we'll talk about those. But the important thing is going to be able to identify, looking at an equation, what has been done to it. Has it been shifted? Has it been reflected? Has it been stretched? Right. And we're going to start with quadratics. Okay, so first thing is a quadratic has the form ax squared plus bx plus c. Okay, that's called the general form of a quadratic. What's important is the coefficients of the x's, a and b. Those have to be real numbers, okay, no imaginaries. And c, the constant, also has to be a real number. But a can't be 0. Because what would happen if you filled in a 0 right there? Yeah.
Will it make that?
It makes that term 0, which would then make that a linear equation. You'd have bx plus c. All right, so you can't have a be 0 and have it be a quadratic. All right. So let's graph y equals x squared. I think we've done it before, but just kind of a reminder of what that looks like. Okay, so I'm just going to type in x squared. I'm going to do zoom 6. And can anyone remind me what's the shape that I get there? That's called a
parabola.
Yep, that's a parabola. Yep. Now, I want to try something a little different. I want to graph the same thing again, but instead of having an x as the variable, I want to replace the variable with a negative x and see what happens. All right. So I'm going to go to y2. I'm going to leave it right where it is, the one that's in y1. And I'm going to put in parentheses negative x. And then I'm going to square it. And I'm going to hit graph. It's the same thing. Now, it's not always the same thing, depending on what kind of sketch you're doing. But, bless you, in this one it is the same. Does anybody know what actually just happened there? And you can't, this isn't a good graph to be able to see what happened because it ends up being the exact same graph. Guess what that negative did. Well, what kind of transformation could you do to the graph and it would end up looking exactly the same as it started? What?
What do you mean, like a reflection?
It is a reflection. Can you be more specific about what kind of reflection?
On the x-axis.
If it was on the x-axis, it would be flipped downward.
Oh. So then on the y-axis?
On the y-axis, yeah. What we just did there is we reflected it over the y-axis, but because the y-axis is a line of symmetry, you can't tell that we did it. Okay. So we'll get a little more detail, but negatives, when you put a negative into some equation, a lot of times that has to do with a reflection. And there's two kinds. There's a negative, if you put a negative in a certain spot, you get a horizontal reflection. If you put the negative in a different spot, you get a vertical reflection. So, as we just said in that graph, the y-axis is a line of symmetry. And this particular graph has a low point. And in a parabola, the lowest point is called the vertex. Now, if you flip it, a parabola can still have a vertex, but it would become the highest point. If you are sketching a parabola and they ask you to find a complete graph, making sure you can see the vertex is important. Okay? You have to be able to see that. So if you wanted to flip that parabola, you could do something like this. The difference is whether the negative is on the inside or the outside of the parentheses. Putting it on the outside, that's going to make a big difference. Okay, that's going to take the parabola, and it does reflect it, but it's a different way now. And just to kind of show you, that will work. Again, we're just studying quadratics, but that's going to work with any function. If you take a square root, second square root, that's the regular square root function. Now I'm going to put a negative in front of it, and I want you to see the difference. The regular square root is going to curve to the right. When you put the negative in front, it causes it to curve to the right, but it's been reflected. Okay. And this is a good one where if I did put the negative on the inside, you would see a difference. Okay. You didn't see it with parabola because the y-axis was a line of symmetry, but in this case, the y-axis is not a line of symmetry. So now, if you look at the blue and the black one, you can see that I've reflected it horizontally. So you can reflect horizontally, vertically, or you can do both at the same time. I'd need two negatives to do that. All right, so now we're going to step away from reflections for a little bit, and I want to see what happens if we change the number that's in front of x squared. So we'll try graphing a few different ones. We'll just try y equals x squared. This is called the parent function. Basically, the parent function is the simplest version, in this case, of a quadratic that you can have. Okay? Y equals 1x squared. That's the simplest quadratic. So let's put in that one, and then we'll do a 1/3 x squared and a 2x squared. Okay, so let's put in x squared. And then to do 1/3, there's a couple ways you can do it. I just do 1 divided by 3 in parentheses, just like that. There are other ways you can type that in. And 2x squared. Okay, we're going to do zoom 6 and look at all three of them. Okay, there's the parent function. There's the 1/3 x squared. And then the last one you're going to see is the 2x squared. Okay. So what's the difference? How would you describe what the number in front is doing to the parabola? Yeah, Nick?
I would say that the bigger the number, the more it narrows down.
Yeah, so it's causing some kind of stretching or compressing. And if we start to make the number bigger, like we did a 2x squared, let's even do one more. Let's do 5x squared. Okay, what's happening is we want to think of this kind of as a stretch or a compression. Some people think of it vertically, some people think of it horizontally. It's up to you how you want to think of it. But the idea is as the number in front of x squared gets bigger, the parabola starts to get skinnier. Okay? If you make the number in front a smaller fraction, okay, we've already got 1/3, let's do 1/10, 0.1x squared. That's going to cause the parabola to get wider. Okay? A lot of times we will think of things in terms of like a vertical stretch or compression. So if you wanted to think of it that way, you could think of like this pink one has been vertically stretched. Okay? Imagine it was like glued down at the origin, and you took the sides and you pulled up on it. Right? What would happen if something's glued down in one spot and you pull up on the sides of it? It's going to get really tall and skinny. Right? It's going to stretch out. If you took and pushed down on it and you tried to compress it vertically, think of like Play-Doh, right? If you squish it down vertically, it's going to spread out sideways. Right? And that's kind of what's happening to the green one. It's like it's been pushed down, so it's spread out. Bless you. Hey, any questions on what that number in front is? Okay, so we saw what happens if we change the number in front. Now I just kind of want to summarize it. So the bigger you make the number, the more stretched the graph will get vertically. What that means is it's getting skinnier. Now if you pick a number between 0 and 1, like a fraction, so we did 1/3, I think we did 1/10, what happens there is the graph shrinks. Right? It's being compressed vertically. It's probably a better word than shrunk. The graph is compressed vertically. Notice here, I'm not talking about A being a negative. If we throw a negative in with A, now we're combining a reflection with a stretch. All right? So for now, we're just talking about stretching vertically or compressing vertically. So A is always a positive number, for now. Now, let's try some of those same graphs again, but let's throw the negative in there and see what happens. Okay, notice where I put the negative. It is in the front. Okay? It's in front of the entire function. It's not inside with the x squared. Okay, so there's a difference if I put the negative on the inside with the x squared, or I just put it in front of the whole thing. Okay. If you want to think of it as parentheses, you can think of that. That's the same thing. Okay. All right, so we got x squared. I'm just going to clear out some of these other ones. Let's do -1/3 x squared and -2x squared. I'll do -x squared as well. Okay, so the first one you're going to see is the parent function, and then all the other ones are going to have some kind of reflection. Kind of want to get a rule for what kind of reflection it is when you put it in front. Which axis did it flip over? The x or the y? Yeah, you flipped over the x. So whenever you put a negative in front of a function, not inside it with the variable, it will cause it to reflect. And I'm showing you 3 different ones. So the first two, the red one and the looks like the red one and the black one, those are reflections, and we're also changing the width of it. Okay, so we're doing a stretch and a reflection. The black one is just a reflection. No, sorry, the pink. The pink one is just a reflection. All right, so let's see if we can summarize that. So the negative symbol causes the parabola to open downward, which means the vertex is a maximum. And that's a reflection over the x-axis. When I ask you to describe it, you could say reflect over the x-axis. You could say flip over the x-axis. Either one of those terms is fine. Again, today we're not going to talk too much about reflecting over the y-axis, just because when you do that with a parabola, if the vertex is at the origin, you won't be able to tell you did it. Okay? When we talk about other graphs that are not symmetric over the y-axis, then we'll talk about reflecting over the y-axis. Okay, so this one is basically asking you to describe the transformations. It's asking you to describe the transformations. There are two transformations here. The 5 is going to do something, and the negative is going to do something. Okay, so we're going to write each one of them separately. Now, the order that you describe the transformations in matters. Okay, I haven't shown you the order yet, so I'm just going to kind of give you a hint how to do it on this one. But eventually, we have to make sure we're doing it in a certain order. Okay, let's start with the 5. So if we go back, look at our notes. Which case does the 5 fall into? Is it case 1 or case 2? Yep, Vanessa. That's case 1. The graph is stretched vertically. Okay? So the way that we're going to describe it is like this. I'm going to say first step to transform this graph into that graph is to do a vertical stretch by a factor of 5. So what that means is if you had a bunch of coordinates on this graph, so you had a bunch of points, you would take all the y values of your points and multiply them by 5. The x's would not change. Those would stay the same. But all your y's would get multiplied by 5. Okay. And the last thing is this negative that's in front. And can someone remind me what's the negative in front going to do? Yep.
It's reflected over the x.
It's going to reflect over the x-axis. Now think about what that means in terms of what you would do to a coordinate. If you had a point at 1, 1, and you reflect it over the x-axis, it ends up down there. What happens to a coordinate when it is reflected over the x-axis? Yeah, go ahead.
The y value changes.
Can you be more specific with how it changes? Okay.
It goes to the opposite. So
Yeah.
if it's in 1, 1, it becomes 1, negative 1.
Yeah, so the y value becomes the opposite. Right. Yeah. So after you multiplied all your y values by 5, you would then make all the signs the opposite. So if they were positive y's, make them negative. If they were negative, make them positive. Right. And that's how you would graph this, starting with that. Any questions on those 2 steps? All right. Now, let's say that you had something like this, 1/3 x squared. And I asked you the same thing. Okay? Describe how you could get that graph starting with y equals x squared. I always start out with this. Vertical stretch by a factor of. What I would do in this one is just say vertical stretch by a factor of 1/3. Okay? So technically, if you stretch something by 1/3, well, it's kind of like saying move down a negative amount. Moving down a negative is almost really like saying move up. So if you say stretch by 1/3, it is really compressing. It is vertically shrinking. All right? But I always word it as vertical stretch by a factor of, and then fill in the stretch amount. Okay? So the stretch amount can be less than 1, and that will compress it. Okay, so again, order is important, but I have a page we're going to get to where I list the transformations and the order you need to describe them in. So we'll get to that. All right, let's look at these two. This time the arithmetic operation is different. It's adding and subtracting. It's not multiplying. And it's on the end of the function. Does anybody have a guess what the +2 is going to do? And again, we're always comparing it to y equals x squared. All right. What do you think the +2 would do to y equals x squared? Lance?
Would it move the parabola by 2?
Move it which way?
To the right.
No, that's not going to move it to the right. We're going to talk about moving to the right. Yeah.
It's gonna move it 2 up.
That's going to move it 2 up. Yep. So to answer the first question, to get y equals x squared plus 2, shift y equals x squared up 2. Yep. And I can show you what that one looks like. All right, so we're going to do y equals x squared plus 2. Hit graph. Okay, there's the parent function. And here's the one shifted up 2 units. That's it. Just shifts it up 2. Okay. How about y equals x squared minus 3? How do you think you'd get that one, Nick?
You bring it down 3.
Yeah, you would shift the parent function down 3. Yep. I'm not going to sketch that one, but you can imagine what that would look like. So adding or subtracting a number on the end of the function causes a vertical shift. Okay, these are different than stretches because they don't distort the picture. Stretches take your picture and it can distort it. When you shift it, that's called a rigid motion transformation. It's just taking what you have and moving it somewhere else. So in order to get y equals x squared plus k from the parent function, there's 2 rules. If this value is greater than 0, you're going to shift up that many units. If that value is less than 0, you're going to shift down. Notice I said shift down absolute value of k units. Why did I put absolute value there when we talk about shifting down? Vanessa?
Because technically you're not shifting down -3.
Right.
You're just shifting down 3.
Right, the down is the negative. We don't want to say shift down -3. Just say shift down 3, shift up 3. Think of the shift amount as a distance. Distance is always a positive number. You just have to say up or down. Okay, so that's how vertical shifts work. Now, I want to look at adding and subtracting again, but now this is different. This is adding and subtracting inside the function that's being squared, not on the outside of what's being squared. So, anybody have a guess what adding or subtracting inside the squaring part is going to do? Yep.
Shifts to the right or left.
Right, it's going to shift to the right or to the left. Okay, so let's start with that first one. Y equals x squared minus x minus 3 squared. Okay, so to get y equals x minus 3 squared. Anybody have a guess what kind of shift we need to do to the parent function? Well, first, how many units do we need to shift the parent function? Yeah. 3. Yeah, we're going to shift it 3 units. Is it going to be 3 units to the left or 3 units to the right? Yeah. Dario?
To the right.
To the right? Okay, let's try it and see what happens. So we got x squared. And now let's see what happens when we do x minus 3 squared. So there's your parent function. And the minus shifts it to the right. Okay, you might think it's going to go to the left because minus 3, you might think it's left, but this is actually backwards. And every horizontal shift that we do all year is always this way. A minus will always shift it to the right, and a plus will always shift it to the left. So to get y equals x minus 3 squared, shift y equals x squared, right 3. And likewise, how would I get y equals x plus 2 squared? We're just going to do this one verbally. Yeah. Shift it left 2. Yep. Take the parent function, shift it left 2, and you will get this one. Okay, so shifting left and right, it's another example of a rigid motion transformation. So there's no distortion. Okay, it's not being stretched. You can stretch and shift at the same time. We're not doing that yet. We will. For now, we're just doing one at a time. And there's different ways you can think about how to remember it. Okay? I always think of my problem like this. So let's say I had something like that, and then I had something like this. If I have a problem that already has a minus in it, then that's fine. If I have one without a minus, I make it a minus. Like that. Okay? When I'm shifting left and right, I always think of it in terms of x minus something. And then what I do is I focus on what comes after the minus sign. In this case, that's a 2. In this case, that's a negative 3. All right, so I always think of it as x minus, and then look at what is after the minus. Since that's a 2, it's going to shift it right 2. Since that's a negative 3, it's going to shift it left 3. Right? So there's different tricks, whatever trick you want to use to kind of keep that straight, that's up to you. But that's how I do it. Always think of your problem as x minus something. And then whatever comes after the minus indicates which way to shift it. If the part after the minus is bigger than 0, you shift right. If the part after the minus is less than 0, you shift left. And identifying h, and the other letter we used was k, that's going to be very important because the h and the k are going to tell you the vertex of the parabola. So you want an easy way to identify the h and the k. All right, I think thinking of it as x minus makes it easy to identify the h because you just have to look at what's after the minus sign. So now, if you put that together, and now it's all the transformations we've done so far, A was a vertical stretch, H was a shift left and right, K was a shift up and down. If you have an equation in that format and you want to identify the vertex, which could either be the low point or the high point, the vertex is always what's in that box, comma, what's in that box. H, comma, K. Not what's in front of H. Okay? Just the H. And if you want to identify the line of symmetry, well, the line of symmetry is only affected by moving left and right. Think if you had a parabola like this. Where's the line of symmetry for that right now? Yeah. Y-axis. Shift it down. Where's the line of symmetry for it now? Yeah,
It's the same.
it's the same. Shifting up and down has no effect on the line of symmetry, which is why K, which is shifting up and down, has nothing to do with the equation for the line of symmetry. Since the line of symmetry for a parabola is always vertical, it's always x equals, and then you put a number. What number do you put? The amount of shifting you did left and right. So x equals h. Okay, so let's see if we can find the vertex and the line of symmetry for a parabola. First thing I'm going to do is quickly rewrite that the way I suggested to think of it. How are we going to rewrite that so we can think of the h, well, especially the h a little bit easier? Yeah.
We would rewrite what was in parentheses as x minus -2.
Yep, we're going to think of it as x minus -2 squared minus 3. Okay. Now we can put a box there and put a box around h. What is h there? Yep. H is -2. That's your h. And what about your k? Ethan, what's my k going to be?
3.
So you're looking in the right spot, but no, it's not going to be 3. -3. Yep. So when we find that, put a box around it somewhere. Oh, I think I deleted it, but yeah. What's at the very end? That's your k. Right, so now the vertex, h, comma k, -2, -3. And how about the equation of the line of symmetry? And it is important you give me an equation, not a number. I need a full equation. Yep, Marcel.
X equals -2.
So yeah, it's x equals h, and h is -2. So x equals -2. If you accidentally put y equals -2, you just gave me a horizontal line. That's not right.
Yeah, it was bad.
Yep, just so now. Okay, any question on finding the vertex or line of symmetry? All right, let's try this one. Now, here's where the order starts to matter, and I need to show you what the order is. If you're wondering, why does order matter? Well, think if you had a coordinate. And pretend like you're throwing your pen on the ground. Pretend like you're changing the x value. If I said to you to multiply the x value by 3 and then add 5, or I said do it in reverse, add 5 and then multiply by 3, is there a difference in the order of operations? Times 3 and then add 5, or add 5 and then times 3. Would that make a difference? Yeah. Take 1 times 3 and add 5. Or take, and do it in the reverse order, 1, add 5, and then times 3. Makes a big difference. So when you're doing transformations, you have to write them in the correct order, or it's not right. So let me give you the order, and then we'll come back and we'll fill in the steps on this one. So here is the order that we want to write down our transformations in. In general, we always do the horizontal transformations first. We're not talking about horizontal reflections in this lesson, so if we were, we could fill that in right in between steps 1 and 2. I'm going to leave it out because we're not doing that right now. So for the transformations that we're doing, step 1, horizontal shifts. If you don't have that, you skip it. Step 2, tell me about any vertical stretching or shrinking that you're doing. If you don't have it, skip it. Step 3, tell me if there's any reflections. Again, these are all if necessary. If you don't have it, you skip it. And the last thing that you'll tell me is any vertical shifting. Okay, so another thing we're not talking about here is any horizontal stretching or compressing. Again, it's just not something we're going to look at with quadratics, but when we get to other functions, I'll add that in. Have to write it down, but if you wanted to know where horizontal reflecting would fit in, it would be right there. And then right after that would be horizontal stretch. Okay, again, I wouldn't worry about writing them down right now. And some of them you can switch the order and it's okay. As an example of this, you can switch 2 and 3. I wouldn't, just leave it in that order. But the reason that would work is because think about if you multiply a number by 5 and then make it negative, or make it negative and then multiply by 5. It's the same thing. Okay, so technically you can switch the order of 2 and 3, but I'm going to stick with that order. Okay. So now, let's see if we can describe the transformations in example 6. Okay, first step, how many transformations are happening? Gregory, how many transformations are happening?
Okay. 1. Because it would be.
Okay, tell me, what are you looking at that's telling you there's 1?
The 5 is getting shifted. Oh, I know, it would be 2, right? Because the 5 and the 4 are being changed.
So the 5 and the 4 are both doing something. Yep. So let's start with the one that we need to. Are we going to start by looking at the 5 or the 4? So this requires you to know what each one of them is going to do, and then look back at the order I just showed you. Yeah, Jane?
What is it, 5?
Yes, we're going to start with the 5. And what does the 5 do to the function?
shifted up,
So what kind of arithmetic are we doing with the 5?
factoring it out,
So arithmetic would be add, subtract, multiply, or divide.
dividing.
Nope, there's no fraction there. If it was dividing, you'd see something with like x squared divided by and then a number. Any other guess what operation we're doing?
Multiply.
We're multiplying. Okay, when you are multiplying, multiplying is never a shift. The only way you can shift is adding and subtracting. Right? So then what does multiplying do? Dan?
Multiplying stretches the.
Yes, that's going to be a stretch. And how would you explain exactly what the stretch is going to be? I gave you kind of a phrase earlier to use.
It would be a vertical stretch by a factor of 5.
Perfect. Vertical stretch by factor of 5. Yep. So that's your first transformation. Now the +4 is the last one. Okay, so I just mentioned adding and subtracting is always a shift, but you need to tell me what kind of shift, the direction, and how much. So what is the +4 going to do? Lance?
Would it be a vertical shift up by 4?
Yep. So you could say vertical shift up by 4. You could also shorten it to just say shift up 4 units. As long as you tell me the direction you're shifting and how much, that's important. If you just said shift up, no, you haven't told me enough. If you just said shift 4 units, no, that's not enough either. So any question on how we got those two or why we put them in that order? Yes?
Why wouldn't it shift like left 4 units instead of up and down? Like,
So if you want to shift left and right, then it has to be added or subtracted like inside the argument, like that. Okay, so adding and subtracting inside the parentheses that are being squared will shift it left and right. Adding or subtracting on the outside of what's being squared is up and down. Okay, so that one, a -3, that would shift it right 3 units. All right, let's try this one. You guys probably are going to have more room below. I have more room up above, so I'm gonna write it up above. All right. Okay, so first thing, how many transformations are happening in example 7? Yep, Declan?
4.
There are 4, yes. So there are 4 different transformations. Okay. What am I going to focus on first? What number, what symbol is the first thing I'm going to look at in that problem? Ethan?
The 1
Yeah, what is it again? It's a
horizontal shift.
It's a horizontal shift, so that 1 is telling me it's going to shift horizontally 1 unit. And can you tell me a little bit more?
It's negative,
Okay.
so it would be to the left.
Nope, when it's negative, when the number after the minus sign right here, that tells you it's going to shift to the right. Okay, so when it's x minus 1, that's going to shift to the right 1 unit. Shift right 1 unit. Okay, so there's your first transformation. What am I going to look at for the second transformation? Yeah, Raj?
The -3.
You're combining 2 things together. So So we're really going to isolate each transformation one at a time.
So the -3 and the.
That's two things you just said. You said -3, right? That's two transformations. So we gotta break that down.
So
Just the 3. Yep, the negative is something totally separate. What's the 3 gonna do?
it's gonna multiply the x.
Well, it's gonna multiply the y's by 3, but we wanna make sure we can write that as like a transformation.
It's gonna stretch it.
Okay, I need a little bit more. Yeah?
It's gonna be a vertical stretch by a factor of 3.
Right, it's a vertical stretch, and it's going to be a factor of 3. So vertical stretch by factor of 3. Okay, so we got that. Now let's look at that negative. What's the negative in front of the 3 going to do? Yep.
Reflect over the x-axis.
Yep, that's a reflection over the x-axis. You could also say vertical reflection. Vertically reflecting means over the x-axis. And the last thing we're going to do is the +4. And what's that going to do to my graph? Nick?
A vertical shift of 4 up.
Yep, so it's going to shift up 4 units. Perfect. So that graph had all the different transformations in it that we talked about. Any questions on that one? All right, so there's that. We already talked about all the transformations. Now, so far, all the examples we've done have been in standard form. Standard form makes it very easy to figure out the transformations. But what if I took this and I changed it? What if I did out the x minus 1 squared? That would give me x squared minus 2x plus 1. That's what you get if you just FOIL out x minus 1 squared. Now, what if I distribute the -3? I'd have -3x squared plus 6x. That would give me -3 plus 4. This, if I put y equals, that is exactly the same thing as that. Difference is, the bottom one, I can easily see all the transformations. Shifting, stretching, and all that. The top one, somebody's done it all out, simplified it. Now, I can't tell what kind of transformations are happening. Like +4, there's no +4 in this at all anymore. So if I give you something like this, how are you going to figure out all the transformations? Well, you have to take this and change it back to that. All right. So the goal when you are describing transformations, at least for quadratics, is you need them in standard form. If they're not in standard form, it's going to be tough to do. If you have something in that general form and you want to change it back to standard form, you need to complete the square. All right, so that's a technique we learn about in Algebra 1, maybe you do it in Algebra 2 as well. A lot of times people forget how to do it, but it is very important. So the biggest thing when you are completing the square is you need to make sure you keep your equation balanced. If you do something on the left, make sure you do exactly the same thing on the right. If you don't keep your equation balanced, then, well, it's not going to come out right. So I'll go through an example. I'm not going to teach a whole lesson on how to complete the square. But I will go through an example and make a few notes as we do it about the steps that we're doing. Okay, so I want to describe the transformations of this. The problem with it is it's not written in the format that I need. I need something like this. A number in front, a set of parentheses, could be a plus or a minus inside. I need an x right there. I need something squared there. And then I need a plus or a minus. That way I'll be able to identify shifting left and right, stretching, shifting up and down. Okay, so we got to transform that. Once you transform it, that's the hard part. Then it's easy to identify the transformations. Okay, does everybody have the completing the square, keep equation balance stuff? Okay. So let's start with this one. So first step to completing the square is to put the constant on the other side. Okay. So we're gonna, well, very first step is we're gonna set it equal to 0. Okay. We already have everything on one side. All the x's are on one side, the constant. So we're basically gonna just put 0 on that side. That's the first step. We already have everything on one side. What I want to do now is move the constant to the other side. How would I move the constant to the left side? Yeah?
Add 18 to both sides.
Add 18 to both sides. Okay, so in this step, I'll just say move constant to other side. Okay, the next step. When you are completing the square, you need the number in front of x squared to be a 1. What is the number that I have in front of x squared right now? Marcelo?
3.
It's a 3. How could I make this a 1? What would I have to do on the right-hand side?
Divide by 3.
Well, we got to do something that still preserves that the 3 is there. So instead of dividing by 3, let's... What can I... Because I don't want to do anything on the left. I just want to manipulate the right-hand side so it looks like the x squared is a 1. We're still going to see a 3. But we just have to do something, yeah.
Just like factor it out.
Yeah, just factor it out. So we're going to be left with 3 on the outside of the parentheses, and then x squared plus 4x. So here, make coefficient of x squared equal to 1. You have to make it a 1. Hopefully your numbers work out nice and you don't have to deal with fractions, but that doesn't always happen. Now, the next step is where we're going to complete the square. We need to add something on both sides. So what we're going to put in that box is like a magic number that's going to make completing the square work. Okay, and the way that you figure out what goes in that box has to do with this number. You have to do 2 things to that number. Does anybody remember when you're completing the square, the 2 things you do to that number? Yeah?
Square root it.
We're going to square it, but we have to do something else first. So you don't have to square root it, but we are going to square it. That's the second step. Something else we have to do to it first. that step? Okay, you need to divide it by 2. If you divide that number by 2 and square it, what do you get? Vanessa?
Oh, divided 4 by 2 squared is 4.
4, yep. So if you divide that number by 2 and square it, you get 4. Now you just added something on the right. Now it's unbalanced. You need to balance it out by adding something in this box. What number would go in this box to balance out what we just did on the right? Yeah?
4.
No, not 4. But a lot of people do say 4 because you think, oh, I added 4 on the right. But you didn't really add 4 on the right. You put a plus 4 in that box, but that's not what you added on the right. Yep?
12.
12. You added 3 times 4 on the right. Okay, so now it's balanced again. So the step here was take coefficient of x, divide by 2, and square it. And add that to both sides. And be very careful, if you did factor a number out, you may not be putting a 4 and a 4 on both sides. All right, so now let's simplify the left. We get 30. And now that is going to factor very nicely. Okay, that's the whole reason why we completed the square. It forces something to factor into 2 things that are identical, like x plus 5, x plus 5. X minus 7, x minus 7. How does that factor? X squared plus 4x plus 4. Yep.
That's x plus 2
X plus 2
squared.
squared. Yes, x plus 2 times x plus 2. Now it's starting to look like that format that we're used to. Factor, I'm just going to say right hand side. And now the last step is put the 30 back on the other side and make it equal to y again. So it's 3 x plus 2 squared minus 30. Now this and what we started with up above are exactly the same thing. The difference is the top one is not written in a format that we can easily figure out the transformations. The bottom one is. If you're not sure they're the same, graph them. Graph the top box in y1, graph the bottom one in y2. They will be identical. Now let's describe the transformations. Okay. Start with the 2. What's that 2 going to do? Yes.
It will shift it horizontally left to
Shift which way?
right to, sorry. But no, left to.
Left 2. Okay, so shift left 2. Okay, what's the 3 going to do? Yeah.
A vertical stretch by factor of 3.
Vertical stretch. It's connecting my writing by a factor of 3. And the last one, that minus 30, is a shift down 30. So any questions on how we completed the square there? Yeah.
How did you get x plus 2 squared?
That came from factoring this. So you have to factor it into 2 binomials. Okay, so that factoring stuff that you learned way back in Algebra 1, yeah, it comes back up here. All right, so yeah, factoring is definitely very important. Yeah.
How is it left to if it's plus?
So plus, remember, think of it like this. Think of the number that comes after the minus sign. Minus 2 shifts it left 2. Yeah, so that's just it. Whenever you see this, it always shifts. This kind of pattern will shift to the left 2. This kind of pattern would shift to the right 2.
But earlier you said that it was the opposite.
So if you look at the number after the minus sign, okay, put a box around what comes after the minus sign. If what's in that box is greater than 0, you shift right. And if what's in that box is less than 0, you shift left. So if we go back to ours. Here's my box. If what's in that box is less than 0, you shift left. So it's however you want to remember it. It is a little tricky at first, but there's different ways you can kind of think about it to remember it. All right. I'm not going to spend too much time on that. So if you want to find the vertex and line of symmetry, there is a formula to do it. I never really remember the formula. If you gave me something like this, and you said find the vertex and line of symmetry, I would just complete the square. Right? And then I could easily figure out, okay, my vertex is at -2, -30. But if you really don't want to complete the square, and they ask you for the vertex, you can use that formula. So why do we bother with the completing the square? Well, if I ask you for the transformations, you're still going to have to complete the square to do that. All right. So these are 2 shortcuts that you can use if you're asked for that information and you don't want to complete the square. But they're not really formulas that I usually use very often. All right, so last thing is for quadratics. When you draw a parabola, how many times could it cross the x-axis at most? Yeah?
Twice?
Twice. Sure. Something like that. Could it cross the x-axis a different number of times besides twice? Yeah?
0 times.
Yeah, could be 0 times. Anything else? Yeah?
Couldn't it be once because of that weird stop thing that I can do in the middle?
Yeah, it could just go up like that, kind of just barely touch it right there, and then come back down. So it could just be once. So when I talk about zeros of a function, I'm basically talking about how many times it can cross the x-axis. It's a number that you can fill in for x. And if you plug that number into your formula, you get 0 for y. That's called a zero of a function. Quadratics have 3 different cases: 0, 1, or 2. Now I'm strictly talking about real zeros. I'm not talking about imaginary right now. And if you have an equation in this format, you can very quickly tell how many times that graph is going to cross the x-axis by looking at this number, that number, and that number. Those 3 numbers will tell you. And what you have to do with those 3 numbers is this calculation: b squared minus 4ac. Does anybody recognize that b squared minus 4ac? Where's that from? Yeah,
quadratic equation.
Yeah, it's the radicand, what's under the radical, in the quadratic formula. So anytime your radicand comes out less than 0, that means you're going to be in a situation like this. Never crosses the x-axis. If b squared minus 4ac comes out to exactly 0, you're going to have a situation like that. Just comes down, touches the axis, and goes back up. If b squared minus 4ac is greater than 0, you can have a situation where it crosses twice. And there's different reasons why we would want to know how many times it crosses the x-axis, but for now, I'm just showing you how you can figure out how many times. What this formula doesn't tell you is where it crosses. So if you want to know exactly where this point is right here, well, then you got to do out the whole quadratic formula. Okay? But if you're just interested in how many times b squared minus 4ac, that will tell you. Any question on that? All right, so that is the homework for tonight on page 56. And we'll take a look at that tomorrow, and then tomorrow we will finish up chapter 1, 1.6. First test will be next academic week. And it'll cover some of what we've done this week, and it'll cover what we do next week in chapter 2.